Welcome back to the course on audio signal processing for music applications. In the previous programming class, we talked about spectral peaks and how to program them, how to detect the values of the spectral peaks. And that was the beginning of implementing the analysis synthesis using a sinusoidal model. So we identify the values of spectral peaks which hopefully correspond to sinusoids. So in this second class, I want to introduce the idea of how to synthesize a sinusoid from those peaks, so how to do basically additive synthesis. So we will be doing it in the frequency domain, like we talked in the theory lecture, in which we are basically synthesizing the main lobes of a Blackman-Harris window and then do the inverse DFT of that. So this equation shows the idea that we synthesize the sound Y by taking the inverse DFT of a sum of main lobes. And in here we see the plot of that. So we see the main lobes already being generated, the phases already being generated, and then we take the inverse of that to generate the synthesized sound. So let's show that. And we first have to actually learn how to synthesize a lobe of a Blackman-Harris window. So in this little code, I show that. So we call this function called genBH lobe, and we give it the samples, the bins that we want to generate. So since we only want to generate the main lobe, we just give the 8 centered bins of that. But first, let's look at this function, genBH lobe, which comes from the util functions file. And in here we have this genBH lobe, which implements the generation of a Blackman-Harris window directly in the spectral domain. In the spectral domain, a Blackman-Harris window is the sum of 4 sinc functions. And this is what this main loop does. It generates 4 sinc functions and it sums them together. Each sinc function has a coefficient that comes from the equation of the Blackman-Harris window. And then in this sinc function, we call a function called sinc, which also is here, which is what generates one particular sinc function. Again, it only generates the main lobe. It doesn't generate the whole sinc function. Okay, so with these 2 functions, we are able to generate the main lobe of a Blackman-Harris window. Let's run this code. Okay, run test2. Okay, and if we show the output X, capital X, these are the 8 samples of the Blackman-Harris window in a linear scale. Okay, so the center is this this 5th sample, which is value 1. If we take the absolute, the log of that, so 20 times log 10 of this X, we will see it in log scale, okay, and we can plot it. So we can plot this, okay, up, and we have one. Okay, so this is the main lobe in the log scale of Blackman-Harris window. If instead of reading these samples, we read some other series of samples, for example, we just add 0.5 to this array, and we save it. And now we run it again, and we plot it. Well, we have to plot. Okay, plot this. Okay, now we see that these are different samples. These are there is no center samples, so there is basically in between 2 samples. This is how we generate main lobes corresponding to different frequencies, because we are moving this main lobe around these samples. Let's now do it with the function that the SMS tools does it, which is the function called genSpec signs. So genSpec signs has as input arrays of frequency, magnitude, and phases, and then it generates a spectrum that includes all that. Okay, so in this code, I am generating one single sine wave at 4,000 hertz, magnitude of 0 decibels and phase 0, and I'm generating the whole FFT of size 512 samples, and then I compute the absolute value, and then here I plot the log of that, so the dV value of that. So let's show that. Let's run test 3. Okay, and this is one main lobe of a sinusoid at frequency 4,000 hertz. And if we zoom into that, we will see, yeah, this is the main lobe. And of course, this has been shifted exactly to have a center around 4,000 hertz. So if we go zooming in more, we will see that the tip of this peak is basically at 4,000 hertz. Okay, now let's talk about how to actually generate the time domain from that. So we have to do the inverse Fourier transform from that, and this is in this other script. I implement that. So after having done the gen spec signs, I call the inverse FFT, and then there is some code to undo the windowing of the Blackman-Harris window. We mentioned in the theory class that in order to have a good overlap at with not much small hop size, it's good to undo the Blackman-Harris window and apply a triangular function. And this is what we do in this part of the code. We generate a synthesis window, which is SW, which is the result of having a triangular window divided by a Blackman-Harris window. Okay, and this is what we multiply by to the inverse of the DFT of what we obtain. So let's run this code. So let's run test 4. Okay, and we can plot the individual steps. So let's plot first the absolute value of the spectrum. Okay, so this is the complex spectrum of the sinusoid. Well, only the magnitude part of that, so that we see both the negative and the positive side of that sinusoid. So we see in here the x-axis is not in hertz, so we don't see the exact values, but this would correspond to the 4,000 frequency, both the positive and the negative side of it in linear scale. Okay. Then what we do is we compute the inverse DFT, so we can plot the inverse DFT of that. So let's plot y, okay, and this is the Blackman-Harris windowed sinusoid in the time domain, in which we see it centered around 0. So we see the second half of the window at the beginning and the first half at the end. There is no zero phase here. Well, there is no zero padding because we actually had the same window size and FFT size, which was 512. Okay, so once we do that, then we undo. We divide by this window and multiply by a triangular window. So we can show the result of that, which is YW. Okay, and this is the signal that we would like to use in the overlap at step, so in which we have divided the Blackman-Harris and we have multiplied by a half length triangular window. So it's only if the original was 512, now it's 256 samples. So we will be able to overlap by half of that. So we'll be able to overlap by 128 samples. Okay, so we have seen the whole synthesis from some frequency values of a given sinusoid. Let's put that together into a real analysis synthesis of a fragment of a sound. And this is in test 5. And in here, we are reading a fragment of a noble sound. And we are going to do the DFT analysis, then we will detect the peaks, then we will interpolate the peaks to get a more accurate value of the location of the sinusoids, and then we will do the synthesis of that in the frequency domain, and then do the inverse FFT and undo the window. Here it plots the spectrum, resulting spectrum, the magnitude spectrum, and the peaks of that. So let's show that. So let's run this test 5. Okay, and this is the magnitude spectrum of the oboe sound, and we have detected some peaks with a given threshold. So let's zoom into that. Okay, and we see the crosses which correspond to the interpolated peaks. Here we see the effect of the parabolic interpolation is huge, because in here we didn't have any zero padding, and the FFT was quite small, so the effect of the parabolic interpolation is really substantial. Okay, so now from these crosses we have the magnitude, frequency and phase of each of these peaks, and we can then compute the inverse of that, and so we can plot the Y array in which has the inverse of that. So here we have the zero-centered inverse FFT of all these sinusoids of the oboe sound. And if we now center it and undo the Blackman and obtain and multiply by the triangular, we can plot the YW, which will be this windowed by a triangular function signal, and this is the one we will be using in the overlap act of the analysis synthesis of the oboe sound. Okay, so that's all I wanted to say. Basically, we have looked another component of the sinusoidal model. We have done the peak sort of synthesis, and before we talked about how to actually find the peaks. And now what we are missing is the putting it all together into a complete analysis synthesis system of time varying and worrying about the continuation of these sinusoids. So this is what we're going to be doing in the next programming lecture. So I hope to see you then. See you. Bye-bye.